against for rapid weather changing are required. We try to rapid weather forecast by new point of view. The forecast of the heavy rainfall and tornado is observation by the detection by radar, but we have only 10 times after the detection. If we can get the initial sign of the cloud generation, it should be the best forecast. Actually, rapid increase of water vapor is the initial sign of the cloud generation. So water vapor is a key for the water vapor is a key for the forecast of cloud generation. It should be the 1 hour earlier forecast. This figure shows the radiation temperature from the water vapor as a function of the frequency. And oxygen radiation is also shown here. The observation at the 20 GHz band gives information about the precipitable water vapor, and 50 to 60 GHz band gives information about the temperature of atmosphere molecular. So we have developing a ground-based observation system. We call it CUMODES. The angular resolution is 2 degrees. It decomposes 50 kilometers away at 2 kilometers. And this picture is a prototype receiver of CUMODES. The requirement for this system is here. One is a high sensitivity receiver for the all sky survey. We aim to observation by at one point in 1 second. For forecast, it is necessary all sky survey is finished in 10 minutes. Second is this system have 20 GHz band and 60 GHz band and observed simultaneously to detect the PWV with high accuracy. Third is the automatic calibration system is necessary to observe the long-term observation. This is the layout of a CUMODES. RF signal is received by the main reflector and transported to each receiver. There is a multi-band dual receivers, and 20 GHz band receiver is a cold receiver and cooled by GM cooler, maintained at 15 kelvins. And 50 to 60 GHz band receiver is a heterodyne receiver and down converted to 10 to 20 GHz. This receiver is an ambient receiver because radiation from this band is strong, and high sensitivity receiver is not necessary. And we employed the black body in the cluster maintained at 45 kelvins. And we operated test observation at the zenith direction at Tsukuba, Japan. This figure shows the radiation temperature as a function of frequency. Left figure shows the 20 GHz band, and right is the 60 GHz band. Each receiver detected the spectrum peaks very clearly. This observation is integration time is 30 seconds. And we check the integration time. We change the integration time. We observed by integration 30 seconds, 9 seconds, 45 seconds, and 0.3 seconds. This is a statistical error for the PWV as a function of the integration time. We can get enough accuracy about a few minutes integration. And also we operated test observation, short time observation before rainfall. And we caught increase of the water vapor prior to the cloud generation. This figure shows the measurement result of the PWV as a function of the time. Top of three picture is optical photo. We started measurement at 9 o'clock, and rainfall is 22 o'clock. So PWV increased from 9 o'clock, and cloud is not there at 20 o'clock. In this measurement, we calculated 4 times using a liquid nitrogen. But it is not sufficient because it is take a long time and is not frequent. So we need the automatic calibration system for long-term measurement. So we employed in-situ calibration system in the cryostat of the 20 GHz band cryostat. And it is maintained at 45 kelvins. And the calibration signal is transported to via wire grid for each receiver. And this wire grid is rotated to select the optical path for each receiver's sky path or calibration signal path. This is a picture of calibration optical system, and this is a rotation stage. When this figure shows the output signal at the 20 GHz band receiver as a function of grid angle. When wire grid angle is 0, receiver receives the signals or sky path only. In this measurement, we put the 300 kelvins black body at the sky path. And when wire grid is 19 degrees, receiver receives the calibration signals only. So this calibration system is frequent. This is a movie of the rotation stage. This grid is rotated, maximum speed is 20 RPM, and rotated continuously. And we operated long-term observation with cold calibration systems. Receiver is installed in the weatherproof like this, and observe the only zenith direction. This figure shows the PWV trends for the half month. Each point is a measurement point in every 2 minutes, and the calibration is every 2 minutes. The gray shadow shows the rainfall time, and we caught rainfall for time. And this detector receives the increase of water vapor prior to each rainfall perfectly. Here, 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 and here. And we have a subjection in future. One is a receiver is a mini model. We change the receiver at the 20 GHz band from GM cooler to the Starling cooler. The purpose is electrical consumption is down to 500 watt, and it is easy to operation everywhere. Of course, cooling temperature is increased to 50 kelvins, but sensitivity is only 20% less. This is a picture of a prototype, and this is a Stirling cooler. Second is we plan to make a 3D map of the PWV. We measured the same position by another detectors. It is a triangulation, and we can get the position of the water vapor, and we can make the 3D map like this. Let's summarize of my talk. We have developing a spectrometer for the atmospheric radiation. It's called CUMODES. It has a cold receiver, auto calibration system, high-speed scanning, and target is a forecast of the cloud generation. Water vapor monitoring with a radio astroscopy, and we operated long-term observation with the prototype system and detected increase of the water vapor prior to each rainfall. That's all. Thank you for attention.
Are there any questions?
So could you go back to the slide showing the design of the... Okay, here. So a couple of questions. So, I mean, the spectrum analyzer is acting as your data acquisition system in some sense. So you are acquiring data through the spectrum analyzer, and then, I mean, this is acting as data acquisition, right? So, I mean, you detect the data through the spectrum analyzer. So
Yes.
Okay. So I have one question. So how stable, I mean, what about the stability of the 45 Kelvin reference?
Stable of temperature.
Yes.
It is 1 or 2 kelvins.
2 Kelvin.
Oh, yeah.
Okay, because I mean, one natural question that you could try to, I mean, if you have an absolute measurement, because in principle, I mean, you should have an absolute temperature measurement.
Mm-hmm.
One of the things you could do, for example, is also measure CMB.
Yes. We measurement the black body temperature and feedback to the when we use the calibration.
I think he said the baseline drift level is corrected those baseline drift. He used a black body calibration. I don't know the number of the stability of that, but it's much stable.
So if you correct for that, in principle, you should be able to recover absolute temperature. So and from there, you should be able to, right? I mean, if you have, if the 45K is sufficiently stable. 10 gigahertz is 10 to 20 is.
No, I mean, it's sure, it's the whole of that, right? Sure, but there is no way you can measure that with this. As a matter of fact, my question,
No, yes, because for the
I'm sorry. In your graphs, the temperatures that you give are referred to zenith everywhere, so they're corrected to zenith? Or do they depend? I mean, because you're talking about trying to do an all-sky survey in order to do, you know, big weather event forecast, right? But then the data that are in your graph have all been corrected to zenith, so is there a zenith dependence taken out?
Sorry?
No, I'm talking about the atmosphere measurement. So the graphs show the value corresponding to zenith everywhere? Or is it?
It's only the change direction. Yeah. Yeah. Yes.
Yeah, but in order to make a CMB measurement, you would be limited by the precision of what you're actually trying to measure, which is the atmosphere.
Yes. Yes.
I was going to say, when I worked with Dave Wilkinson at 20 gigahertz many years ago, we were actually able to predict even the formation of clouds by just looking at the RMS value rising. So typically the RMS was about 20% above theoretical, and the moment it went above a factor of 2 times theoretical, we knew a cloud was going to show up, sometimes hours afterwards. So I suppose by the time that you're actually worried about the big clouds that you see developing storms, by then the atmosphere is very inhomogeneous. And so the first question is, how do you actually determine the zenith behavior of the atmosphere? Because at that point, doing zenith scans is probably not possible, right? Okay.
Any other question? I have another one. So, what model do you use? Because you measure zenith temperature. What model do you use to estimate PWV from the atmosphere temperature? Is it AM or?
We use AM atmosphere model.
Which one?
AM atmospheric model.
Okay. So if there are no more questions, let's just thank Taketo again.